Well, this is part 2 of the photoresistor A to D demonstration. In the part 1, we looked at the hardware, how to connect the resistors, the photoresistor, a voltage divider, and the tap of the voltage divider we are sending to port C bit number 0, which is channel 0 of the ADD converters. So once you have the hardware set up, and also, I should not forget to add, and this I probably should have put in the first video, but I want to emphasize that we have to connect the V reference, and the V reference needs to be set to 5 volts. This pin, it's in hardware, needs to be set to 5 volts. It is located 2 pins away from PC0. So let's not forget to set the V reference. It's well, if you don't do it, it won't work. Here we go. Ready? Okay. So once again, in the hardware we have the analog voltage from the voltage divider going to port C bit number 0, and we also have the V reference on the chip going to 5 volts. Then at this point we can write our software. So I started a new program, as you can see here, in C, and you need to have these 3 lines as I'm showing you here. The first line is to disable the inputs going to port C. It disables the digital inputs. The digital inputs going to port C. Then the second line selects the channel for the AD converter. This selects channel. Currently it is selecting channel 0. If you want channel 1, you would set this to a 1, and that would select channel 1. We have 6 channels altogether. They're numbered 0 through 5. But I want channel 0, so I change the AD mux to a 20 in hex. Then thirdly, we have the ADC SRA. And this does, well, for one, it turns on the ADD converter. And so this line that has the ADC SRA equal to a C0 turns on the ADD converter, and it reads the ADD converter just one time. When it reads the ADD converter, the register ADCH has the value, has the answer. And this value then goes into the variable called X. So this reads the ADD converter. For example, if the voltage was 1 volt going into the ADD converter, that's 1 volt out of 5, so that's 1/5 of the total, and the total would be a 255 maximum. So 1/5 of 255 is 51. And that's what you would get. Alright. And that what value 51 is in ADCH, and that then goes into the X. Well, very often you want to make more than one measurement. So the other value that you could put here in the ADC SRA is a E0, and this turns it on and reads it forever. Reads continuously. Continue. So I'm going to read the ADD converter continuously, and so it makes more sense then to put the instruction here for x equaling ADCH into a loop. So I'm going to put this into an infinite loop, so it'll continuously read the ADD converter. Even though the ADD converter is continuously reading, you have to then actually get the values out of the ADCH, which is what I'm doing in my loop. So here's an infinite loop, and in the loop, which runs forever, I'm reading the value for X from the ADCH. Yeah. The next thing I want to show you with the program is that the ADD converter does take some time to compute the result. So we need to put a delay here between turning this thing on and actually making a measurement. Let's go back to reading this thing just once, which is a C0 for the ADC SRA. When the ADC SRA is a C0, we read this thing just once. Reads once. But you can't just go from that line to the X equals ADCH. You need to delay for the appropriate amount of time so that the ADD converter can make a measurement. So you're going to have to do a delay here. And one thing that you could do is you could delay for 1 millisecond. And that would be plenty long enough for the converter to make its measurement. In fact, too long. Well, I shouldn't say too long, but you know, it's plenty long. It's more than we need. Also, my program, I haven't written the subroutine to make the delay, which would go down below here. So you'd put it down here, you'd put a delay routine for 1 millisecond. And that certainly would work. You know, so as shown here, this is fine, assuming that you put a delay for 1 millisecond. I'm going to write that delay subroutine for you. Okay, so now we see the delay subroutine that I typed in. Again, we need the delay subroutine between the turning on the ADD converter and reading the ADCH. If you don't have the delay routine, you won't get the proper value. So I put in a delay of 1 millisecond, which is plenty long, much longer than we need actually. With a delay of 1 millisecond, we could make about 1,000 measurements per second, because the microprocessor runs at 1 megahertz and this is 1,000th of a second. The looping of 54 times in a for loop is equal to a millisecond. I've done the calculation using the simulator. So using the simulator, I was able to find out that the 54 loops is a millisecond. Now if you try to build this, it's not going to compile because you need to take the first line of the subroutine and copy it and paste it up here and have it as a prototype. So I'm going to copy, paste, and then put a semicolon after it, and this should then be fine. Okay. So I put the prototype up there with a semicolon for the subroutine, and then I built the program to make sure that there were no errors, and it looks good. There are no errors, and this is an example of one of the smaller programs that you could have to read the ADD converter. In the next portion or part of this video, part 3, I'm going to show you how you could reduce the delay to a much shorter delay and make it more efficient time-wise.